Welcome to our video where we're going to do a couple of percent composition problems. The first one that we're going to do, if you're in my lecture at Siena Heights University, is going to look familiar. The numbers have changed a little bit because it turns out the numbers I used in lecture don't quite give us the right answer. So we have changed that. And the second problem we're going to do, higher degree of difficulty, is the one that was assigned during lecture. So those are the two we're going to choose to do today. And here are the values for the first one that we have found. We are given 64.88% of our compound is made up of carbon, 21.61% is oxygen, and 13.52% is hydrogen. We're also given at the beginning of the problem, rather than springing it on you at the end as I did in lecture, that the molar mass of this compound was determined to be 222.1 grams per mole. We don't need that yet. We're going to use that at the very end to convert from an empirical formula to a molecular formula. So let us begin. The first step in doing these problems is, as we said in lecture, if we add up our percentages add up to 100%. So we're going to imagine that we have a 100.0 gram sample, and that allows us to assume that for carbon we have 64.88 grams of carbon. For oxygen we have 21.61 grams of oxygen, and for hydrogen we have 13.52 grams of hydrogen. And now that you're being trained to be a chemist, you know that once I have grams, I can convert them to moles by using, in this case, atomic masses. So for carbon, we know that 1 mole of carbon has a mass of 12.01 grams of carbon. That's readily available on the periodic table. That oxygen, for 1 mole of oxygen, that is 16.00 grams of oxygen. And for hydrogen, that 1 mole of hydrogen is 1.01 grams of hydrogen. All right, so our units, all of our gram units will cancel when we start doing a little bit of algebra. And we can now do our math, where we have, and I'll highlight this, the 64.88 is divided by 12.01. So we have 5.402 moles of carbon. Our 21.61 is divided by 16.00. So we have 1.351 moles of oxygen. And our 13.52 is divided by 1.01. So we have 13.386 moles of hydrogen. And now that we have moles, our next step is to go to determining our mole ratio. So how do we do the mole ratio? We're going to divide each one by the smallest. So for carbon, we're going to take 5.402 and we're going to divide by the oxygen value, 1.351. And we're going to get that our ratio for carbon is 3.998. And at this point, we will allow rounding. That means we have 4 atoms of carbon. For hydrogen, we have 13.386 moles divided by the smallest, 1.351. So we have 9.91 is our mole ratio, and we're going to round that up to 10. And then finally for oxygen, it's 1.351, and we're going to divide by the smallest, which is oxygen. So that gives us a mole ratio of 1. So now that we have the mole ratios and they're each a whole number, it's a beautiful thing, because now we can write that our empirical formula is C4H10O. Empirical formula. Now remember, if we scroll back to the top, we were given what the molar mass is. Since we're given the molar mass, we can determine what the molecular formula is. And how are we going to do that? Well, from the empirical formula, we need to go to the empirical molar mass. And I like to do things systematically, as you know. So we have carbon. We have 4 atoms of carbon times 12.01 grams per mole. For hydrogen, we have 10 atoms times 1.01 grams per mole. And again, our atomic masses are from the periodic table. For oxygen, I have 1 times 16 grams per mole. So this is 48.04 grams per mole from carbon, 10.10 grams per mole from hydrogen, and 16.00 grams per mole from oxygen. And if I add those together, our empirical molar mass is 74.17 grams per mole. So I have 2 molar masses, and what do I do with those 2 molar masses? Well, we're going to determine what our multiple is, and in lecture we called that N. And the way we got N was we took the formula, or let me use the right word, the molecular molar mass, and we divide it by the empirical molar mass, and that gives us the multiple N. So in this case, our molecular molar mass was 222.1, oh, sorry about that, grams per mole, divided by our empirical formula mass, 74.14 grams per mole. And that comes out to 2.996. And again, we can round. So we get that N is equal to 3. And what does that mean? Well, what it means is we have to take our empirical formula, C4H10O, and we need to multiply that by 3, so our molecular formula is C12H30O3. And as a check and balance that I will talk about a lot, you can check the molar mass of this compound to assure that it's 222.1, and I can pretty much guarantee you that it is. All right, so that is our first, probably more straightforward kind of problem. So the second one we're going to do, we need to do a little more work. And the compound we talked about, magnetite, as one of our examples in lecture that I would have went to the board to do, so I'm going to do it here. Magnetite is made up of only iron and oxygen. And we are told that it is 72.36% iron, and we want to know the empirical formula. So the first thing we need to do is, if we have the percent iron and we know there's only 2 elements, all we need to do is start with 100% and subtract 72.36% iron. And that will give us that we have 27.64% oxygen. And now we have percentages for each one of the components, so we can go through the process. First thing is, we're going to turn our percentages into grams, assuming we have a 100-gram sample. So for iron, we have 72.36 grams of iron. And for oxygen, we have 27.64 grams of oxygen. And you're a chemist, so what do you do when you have grams? We're going to go to moles. Iron, 1 mole of iron has an atomic mass of 55.84 grams of iron. And 1 mole of oxygen, and by now this is getting in your memory, 16.00 grams of oxygen. The gram units cancel, and we find out that when we take 72.36 divided by 55.84, that we have 1.296 moles of iron. And when we take 2764 and divide it by 16, we have 1.728 moles of oxygen. Once we have the mole of each component, we need to get the mole ratio of our compound. Well, what's that going to be? Remember, we have to divide by the smallest one. So, iron, 1.296. Oh, that is the smallest one, 296. So iron is 1.00. Oxygen, we have 1.728 divided by 1.296, the smallest. And that ratio is 1.33. And this is why this problem has a higher degree of difficulty than the first one. Because we have mole ratios. We have 1 mole ratio, the oxygen one, that is not a whole number quantity. And we haven't had to deal with this in the past. So what are we going to do? Well, we have to make it a whole number quantity. And basically, we have 1 1/3, or we have 4/3, okay? So what do you think we're going to need to do to turn 1.33 into a whole number? Well, the hint is if you write these as a fraction, the hint is in our choice of denominator, or the denominator that we are given. We're going to multiply this by 3. And 1.33 multiplied by 3 is 3.99, and we're going to round that up to 4. Now, do we only multiply the oxygen because it wasn't a whole number? No. Remember, the iron and the oxygen are in this together. So whatever we do to one, we have to do to the other one. So we have to multiply the iron by 3 to give us that the mole ratio for iron is 3. And when we write the empirical formula, it is Fe3O4 is our empirical formula. And just as we close here, I just want to give you something to think about, that if our ratio had some other fractions that are very common, we would have to multiply by different numbers. 1.25 is really 1 1/4, so we would multiply by 4, and that would morph into 5.00 for our mole ratio. If we had 1.5, that's really 1 1/2. We would multiply by 2, and the 1.5 would become 3. And the most important thing possibly to remember is all mole ratios. Computer's acting up, folks. all mole ratios must be multiplied by the same factor. So you thought that algebra and that geometry stuff you learned wasn't going to be important, but here it is. Because there are multiples of all the atoms involved. You can't just double one and leave the other one the same. No, they all double so that the ratios wind up being whole number quantities. So this winds up being a pretty important thing to remember, is all the mole ratios have to be multiplied by the same factor. If you didn't get it, watch it again. Do your homework, do your practice, do your reading. Get help if you need it. And we'll see you next time. Bye-bye.